Hello and welcome to the GeoRGB community. This is the first lesson of the Conditional Gaussian Simulation course, and the topic is Gaussian Anamorphosis. Gaussian Anamorphosis is a kind of data transformation that we have to apply when working with Conditional Gaussian Simulation, because one of the primary assumptions of the Conditional Gaussian Simulation is that the data is following a Gaussian distribution. In today's lessons, we are going to explain what Gaussian anamorphosis is and how it works. We'll show you how to apply this data transformation technique using the software R and how to automate this process using R integrated with QGIS. In this way, you will be able to apply Gaussian anamorphosis to any data set loaded in QGIS. Let's learn together. First, let's go to load some libraries in R. Now I'm going to load the data set, that is the Muse dataset, and this data it's integrated inside the library SP. And this library is to work with spatial features. The GeoStat library is to do some geostatistics, for example, for the creation of semi-variograms, for the Kriging interpolation, and other things. And these two libraries are related with the creation of the graphs. It makes more easy to put two graphs together, okay? Now, if we see over here, we can see that we have the data set in this panel, and it's saying that we have 155 observations and 14 variables. Then we can double click over here to open the table. In this table, we have several variables like the UTM coordinates, several heavy metals, and other variables related with elevation, distance to the river, organic materia, and other parameters. But today we are going to be working just with the zinc concentration. The zinc concentration is in ppm. Then the next step is to extract the values of the zinc from the table with this script over here. And then we are going to have the values in this side of the panel, like zinc, as you can see over here. Then the next thing is to create a simple histogram to see the data distribution of the zinc concentration. To do that one, we are going to use this script. In order to make limits on the histogram, we are going to use this sequence over here. Then we are going to say that the maximum for the zinc concentration is 1839, the minimum is 113, and when we make the difference between these two values and divide it between 12, we are going to have the width of each bin on the histogram, okay? Then we can run this script over here. Also, we can plot the mean value and also the median. The maximum and the minimum values, you can get that ones on the table, right? Minimum is 113 and maximum 1839. The histogram has 12 bins as we indicated over here, and what we can see is that there is a big skewness to the left. The majority of the samples are ranging from 113 ppm to 250. The frequency in this case is the number of samples. As we can see, we have just a very few samples that has a value bigger than 1000, but a lot of samples with a value between 113 and 250 ppm. This asymmetry on the histogram is indicating that there is no normal distribution on the data. Then we have to apply here a Gaussian anamorphosis in order to have a normal distribution in our data set. The next thing I'm going to do is quantify the mean, the median, the standard deviation, the minimum value, and the maximum value for our data set. And I'm going to put all these values in a data frame To do that one, we are going to use this script. Then we can run here. And now we are going to add all these values inside of a table. To do that one, we are going to use the next script. The next thing I'm going to do is plot the table. And here we have the values. For the mean, we have 469. For the median, we have 326. The standard deviation is 667. The minimum value and the maximum value, we know that ones because we saw already on the table. The next thing is to create the empirical cumulative distribution function related with the zinc concentration. Then I'm going to run this script. And now I'm going to plot that graph. As this graph is not really nice, as you can see, we can do the same graph, but using the ggplot2. Then I'm going to load the library, and I'm going to create the same graph, but using ggplot. Now, if we run this script, we can see the graph in ggplot. And this graph, as you can see, is more nice. At the end, the cumulative distribution function is the summation of all the bins for each sample. I'm not going to go deeper in the explanation of this graph because I already did. Then if you want to know more about the cumulative distribution function, just go to the YouTube channel of the GeoRGB community. Then in the lesson 3, of the first geostatistics course, this lesson over here, we explain already what is the cumulative distribution function. Then here is everything explained related with this graph. I recommend to watch this lesson in order to get more informed about the cumulative distribution function. Then the next thing that we are going to do is to simulate a data set. In this data set, we are going to have 10,000 samples, and we are going to simulate that this data has a mean of 0 and a standard deviation of 1. My intention is to compare the cumulative distribution function that we have with the original data, with the Muse River data set, with this data that has been simulated with these characteristics. Then we are going to run this script. We are going to generate the new data, and with that data, we are going to create also a histogram. And this histogram is going to have also 12 bins. And we are going to plot also the mean and the median. And as you can see in this histogram, is showing a shape that looks like a bell, indicating the normal distribution of this data set. Also, we can plot here the mean value, the median, the variance, and the standard deviation. And as you can see, the mean and the median, they are very close to 0, and the standard deviation is also 1. And that's the goal that we want with our original data. The goal is to have a histogram like this one. Let me show you. I want this histogram to become the same as this one here. And how we can do that one? With the accumulative distribution function. Let me show you now the accumulative distribution function for this data. And I'm going to plot that one. I'm going to do that one with ggplot as we did with the other one. And now I'm going to put the two graphs together. And let's go to make this one bigger. This graph is the cumulative distribution function for the zinc concentration. And this graph is the cumulative distribution function for a Gaussian distribution. It's a perfect normal distribution. And how we can make this data set to become like this one with Gaussian anamorphosis. And that's what we are going to see now. I created a slide for see this one. Then in Gaussian anamorphosis, the objective is to transition from a random variable x with a no cumulative distribution function. This variable x in our case is the zinc concentration, to become a new random variable z that is going to be a different variable, okay? Because when we are doing Gaussian anamorphosis, we change totally the distribution of our data. It becomes a different variable, okay? And this new variable, the objective is to have a cumulative distribution function that is the Gaussian one, that is this one. Then this function, the f with the capital letter, is the original cumulative distribution function for the variable x, is this function over here. And this function with the g with capital letter is the function associated with the cumulative distribution function of the Gaussian distribution. And this is the function for the probability. And here we have the equations for performing the forward and backward transformation. Then in this case, to transform the variable x to the new variable z, what we have to do is take the original function, f capital letter, that is this function over here, and go to the inverse of the Gaussian cumulative function, that is this one. Then we go from the original cumulative distribution function to the inverse Gaussian cumulative distribution function. And that's what we can see in this graph over here. For example, we have a value that is around 200 ppm. Then we go up, we see what is the probability. In this case, is the probability for the first quantile, that is 0.25. And then we go to the Gaussian cumulative distribution function, and we can see that the equivalent value is going to be minus 0.8 approximately. And that's the equivalent value that we have for the Gaussian cumulative distribution function. And another important thing here is when we created this graph over here, it's not a real function because, as I said previously, it's the summation of all the bins for each sample. Then we have to create a function here. How we can create this function? Using Hermite polynomials. With these polynomials, we can fit here a different number of polynomials, trying to adapt to the shape of the graph in order to have this function over here. However, for the Gaussian cumulative distribution function, we don't need to create any function because the function related with the Gaussian distribution is very well known, okay? And then that's for the forward transformation, but for the backward transformation is the opposite. We have to go from this one to the other one. And that's how we can do the transformation and back transformation. Now let's see how we can do this transformation using R. Remember that if you want to have full access to the course, just go to the GeoRGB community website at giscourse.online. Click on the course, in this case the Conditional Gaussian Simulation. Then get enrolled in the course and then you will be ready to start learning. Clicking on Start Learning, you are going to have access to the lessons. At this moment, I have just added the lesson number 0 that is related with the introduction to the course, but you are going to see the lesson number 1 that is going to be for the Gaussian anamorphosis. Then go down and here you have different labels. Then you have to select exercise files and here you are going to find the Conditional Gaussian Simulation for the lesson 1, for the Gaussian anamorphosis, the scripts. Then you can click here to download. I put this file here as example, but I'm going to remove this one because this one is from the lesson number 1 and it's not for this lesson. It was just an example to see how you can download the scripts and coding that we are using for the lesson. The package that we are going to use to do the Gaussian anamorphosis, it's not located at the repository of CRAN. Then what we have to do is to load the package directly from the website. and now it's already installed. Now I can run the library. Then I'm going to run this one, and now we have the package already loaded. Now I'm going to create an object where I'm going to indicate where is located the coordinate X, where is located the coordinate Y, and where is located the variable that I want to transform. Okay, that it comes from the Muse River dataset. This one is the column 1, column 2, 3, 4, 5, and 6. And that's the information I added here. Column 1, column 2, and column 6. It is like a standard database according to this package, okay? But it's like an object, doesn't matter. The terminology is not really important. Then we can run this script. We can see the class for this object. Also, we can print some information related with the object. And now we are going to define the model for the Gaussian anamorphosis. Then we can run this script if you want to know how to create this object with the help. But now I'm going to create this object with this name. With this script, we are going to define the model. And in this model, we are going to use the type that is going to be Gaussian. And the important thing here is the number of polynomials we are using to define the function, as we said previously. As more polynomials you are added, it doesn't mean that you are going to improve the function, okay? You have to play with this parameter in order to have the best results, okay? We are going to see now how you can do that one. Then we can run this script. And now the next thing that we are going to do is, according to this model, we are going to transform the data. Now, for example, if we change the number of polynomials, let's go to put 10, we are going to have a different function, right? If, for example, if you put 2 polynomials, it's going to be very poor, and the function is not going to be well adapted to the cumulative distribution function. We are going to see now one with 2 polynomials. As you can see, it's not really good. With 3 polynomials, still not good. I was checking for several polynomials. What I saw is with 43 polynomials, it's pretty good, the results. You are going to see also the results when we are doing the histogram and when we are checking the values for the mean, for the median, and how is the shape of the histogram. Then if doesn't convince you, you can still change the number of polynomials in order to have good results. Now, as I know this number of polynomials is good, I'm going to proceed with the data transformation. Then this object has inside the data transform. Where is located this data transformation? In the column number 5 of this object. I don't know if we can print this one. Let me see. Copy. Paste here. And let's go to see if we can see this object with the print information. As you can see, the column number 4, that in reality is the number 5 because it is the 0 number, then is 1, 2, 3, 4, 5 is the value for the transformation. And that's what we added here. With this object, in column number 5, we want to create a histogram with 12 bins. Then I can run this one, and here we have the histogram with the data transform. As you can see, this histogram is pretty symmetric, okay? And it's really good. It is showing a pretty normal distribution, okay? Then I want also the mean value, the median, and I want that show me the curve for the probability density function. Now the next thing I'm going to do is to extract the transform values from this object, assign this name, and then put on the Muse River dataset, in this dataset, add a new column with the transform values. Then to do that one, I'm going to use this code over here. And now if we go to the Muse River dataset, we are going to see that now we have a new column with the transform values associated with the Gaussian distribution for our dataset. Then the next thing is to plot the histogram with ggplot for this new data. I'm going to use this script over here. It's pretty similar as the other one, but it changed a little bit the things, right? Almost is the same. But here with ggplot, you have more options to make more modifications on the graph. Now with the next script, I'm going to say that these values are come from here, from the Muse dataset, and for this column. This is the dataset, or the data frame, and this column. Then I'm going to run this script to add the values on this panel over here, as you can see. And now I'm going to create a data frame with the parameters of the mean, median, standard deviation, minimum value, and maximum value, as we did previously with the original data. Then I'm going to create a new data frame. This one is going to be my table number 2. Now I'm going to convert this table to plot the table in a graph. To do that one, I'm going to use this script over here. And now I'm going to plot the graph. And as you can see, with this new data transform, I have a mean of 0, a median of 0, a standard deviation of 1, and as you can see, the histogram is pretty symmetric because we have a minimum value of minus 2.8 and a maximum value of 2.76. Then if we compare these results with the first histogram that we get, the difference is too big, right? Let me show you. This one, it was the first one, where we have a total asymmetric histogram, but after the transformation, we get a histogram that is showing a perfect Gaussian distribution. I cannot show the next one. There we go, this one. Now the next thing is how we can create a script to be used in QGIS in order to automate this process for any data set that we load in QGIS. I already opened QGIS, and now what I'm going to do is to load the Muse River dataset on QGIS. Then if you don't know how to extract this dataset from R to be open in QGIS, my recommendation is to watch the second lesson of the first geostatistics course. Is this lesson over here, this second lesson. In this lesson, I explain how you can get the Muse River dataset to be open in QGIS. It is pretty easy. It's just to write a code here to extract the dataset in a CSV format, and that's what I have over here. Have here some datasets from the previous lesson, and concurrently here I have the Muse data in CSV format. Then I'm going to open that one over here. It's going to be this option, and it's going to be this dataset. Open. You have to make sure that you have selected this option. The X and Y, they are good. The reference coordinate systems is good. This is the data that we are going to open in QGIS. Then we have to add. This is okay. And close. And now here we have the Muse River dataset open in QGIS. Next, what I'm going to do is to create the script, then create a new R script, and I'm going to paste here what I did already. This is a very long script because it has a lot of graph incorporated. First, I'm going to save with this name. Cut. I'm going to remove these two rows over here, save as, and I'm going to save in this folder. Remember that this folder is the one it comes by default with the R scripts. Then paste over here the name and save. Now let's go to explain a little bit what we have in this script because it's a very long one. First, all this section is related with the QGIS interface. The first thing is a subfolder where we are going to save this script. In this case, that subfolder is called as a simulation, okay? Then the second line is related to plot the graphs in a browser. Then all these ones are related with the Windows interface that we are going to use to add all the information related with our variables, okay? Then the first one is for add the vector layer or the CSV file. Then the next one is the variable that we are going to work to do the transformation. These two are related with the X and Y coordinates. This one is to add the label for the X-axis of the histogram. For each variable, this name is going to be different. That's the reason because I put this option to add the name. In my case, it's going to be the scene concentration. Also, for the title, you can add any title you want. In this case, what I'm going to add is a Gaussian Anamorphosis. Then these two lines is for adding the minimum and maximum value of your variable, okay? In this case, it's going to be for the scene concentration, and the minimum value is 113, and the maximum value is 1839. But you can add the values related with your variable. This one is for the number of polynomials that we want on the Gaussian anamorphosis. Then you can change, and then you can try different values in order to see what is the one provides the best result. This one is for the number of bins that we want on the histogram. And the last one is because in this script also is going to generate a CSV file, okay? It's going to generate a spreadsheet with the X and Y coordinate with the original value of the variable, in this case the scene concentration, and also another column with the transform values. And we are going to use that spreadsheet to do the simple kriging and also the simulations. Then the next thing is the libraries that we are going to use with this script. But this is very important that we have to verify that the 64-bit box has been checked, okay? Then we have to go to settings, options. Here in providers, we have to go to R and make sure this box is checked, okay? Because this is very important. In other way, the libraries are not going to be loaded well, okay? It is necessary. Then okay. And then we can go to the script. Now the script is already over here. As I said, is the subfolder, is the simulation. Then edit. And we can continue with this script, okay? Then we check this one already. Also, we have this option here. If this library doesn't work well, because it's already installed in R, but if it doesn't work well, the script we can install through QGIS. And this is the script that we are going to use in that case. Then the next thing that we have is the graphs that we are going to create. First, for the raw data. First is going to be for the scene concentration without any transformation, okay? And then we are going to the histogram. And for the histogram, we have this script that it is a ggplot script. Then we have the cumulative density function, again, for the original data. That's also a ggplot graph. Then we have the probability density function, is this script. And then we are going to do the same, but with the transform data, okay? With this script, we are going to create the object, then we are going to define the model. We saw already these ones with R before, right? Then we are going to do the transformation, and we are going to extract the values, and we are going to create the same as we did with the original data, but in this case, with the transformed data. We are going to do the histogram. We are going to do the cumulative density function. We are going to do the probability density function. And then we are going to create a table. That table is going to be plotted. First, we are going to create that table for the original data with the parameters, the mean, the median, the standard deviation, the minimum value, and the maximum value. And then we are going to do the same for the transformed data. Then we are going to plot these two tables on the graph also. And at the end, we are going to put everything together in just one graph. And the last thing that we are going to do is create a spreadsheet that we are going to export with this script over here. The spreadsheet is the one I told you before, right? With the X, Y coordinates plus the zinc concentration plus the transformation of the zinc concentration according to the Gaussian anamorphosis. Then now we can try to see if this script is working. My concern is this one over here. Maybe we have to use this script in order to install this library through QGIS. But first, let's go to see if it works. Then we can close this one, go here, double click to open the script, and let's go to add the variables. Here the parameter is going to be the zinc concentration. This one is the X coordinate, this one is the Y coordinate. The label is going to be the zinc concentration in ppm. The title of the graph is going to be Gaussian Anamorphosis. As I said, the minimum value is going to be 113. We can check that one on the attribute table. Go here, zinc, maximum. This is the minimum, and this is the maximum. Minimum and maximum. Then that's the values I want to add here. And also here. The number of polynomials, at the moment I'm going to try 45, for example. Number of bins, I want 12. I want 12 because if I do the calculation, let me show you with the calculator. This one, what we have is 155 samples. If we check here at the attribute table, in total this one is number 1. And we have 155. Then if I do the root square of 155, what I get is 12.4. This is approximately 12, and that's the bins I'm going to add. That's the way I calculated the number of bins. Then also I want to save the spreadsheet. Then I'm going to select a folder. It's going to be, let me check here, desktop, simulation, Gaussian anamorphosis, and I'm going to save the spreadsheet here. Data transform. 1. Save. And I'm going to try to see if it works. Okay, as you can see, it cannot recognize this library. Then I'm going to do what I said previously, right? Then edit a script. Then I'm going to take the pound here because I want to install the package, and I have to change this one because this one is going to be different. Then I have to look for where I leave that package. Then I go to the desktop, simulation, Gaussian anamorphosis, and I put here inside. I have to copy this one here, copy, and I have to paste over here. paste, then I have to change these ones for the different direction. And also I have to change the name of the file because here is different. Then rename. I'm going to copy everything. Close. Go here and put that name here. And the rest is good. And now I'm going to try to run again this script to see what's going on. Save and close. And now I'm going to try again. As you can see, again, it's not working. I'm not sure what could be happen now. I'm going to restart QGIS to see if the problem is solved. I have to figure out what's going on and then I will tell you. Okay, I already fixed the problem and I'm going to tell you what I did. Then if I go to the script, simulation, open script to edit, then what I did is remove the library, okay? I cut it, I save, and I run the script like that, right? Then I'm going to put this one again, save, and after running the script without the library, I get the package to be installed. And I'm going to show you the screenshot I took. As you can see here, it's saying the package successfully unpacked, okay? Then, well, I did that one, I get the packet to be installed. I don't know why, but when I have the library put it doesn't work well. But then after remove it, I get the package to be installed. Then I run the package again with the library and it works. And now the script is working perfectly. I did that one because I have the same issue when I was working with my main computer, when I was trying to figure out why the script doesn't work, because it happens also to me at the beginning when I started to prepare this lesson. And I didn't remember how to fix it. But then it comes to my mind that I did that one. And it works. I don't know why. I don't know what is the reason because of that, but it's working now. And that's what we are going to see now. The simulation, double click to open the script. Again, let's go to add the parameters. X, Y. This one is the scene concentration. This one is Gaussian Anamorphosis. This one is the minimum value, 113. Then here we have the maximum value, 1839. Here is the number of polynomials, 45, I said. Number of bins, 12. And at the moment, I'm not going to save this one. I'm going to leave as a provisional. Later, well, I'm going to save, but I'm going to put 43 polynomials. That is the good one. And I'm going to save here. In this folder is good. Data transform. And it's number 1. Save. And now we can run the script. And 3 things. First, here we have added the table that it was created. Let me show you the table. Then in this table we will have the X and Y coordinates, the value of the scene concentration, and the transform value according to the Gaussian anamorphosis, okay? Then another thing, here we have the graphs. Double click to open in a browser. Let's go to make this screen bigger. And then here we have the original data with the histogram, and this one is the transform data. Here we have the cumulative density function for the original data, on here for the transformed data. Here we have the probability density function for the original data, and here for the transformed data. Here we have the values for the original data, and here we have the values for the transformed data. And also, we have here the spreadsheet. Let me see, desktop, simulation. We save inside here, I believe. Data transform is this one. We can open this spreadsheet and okay, open as a copy. And this document can be also opened with Excel, the software Office. Then we can close this one. And now we can play with this parameter, the number of polynomials, in order to see what is the best option. For example, if we put here number, I don't know, 6 polynomials to define the function, you are going to see that the results are not really good. Now double click to open. The problem is that I didn't remove this one here, and now it's going to save also the spreadsheet. But this one is the result. Then what you can see here, okay, we have a mean and median that is close to 0. We have a standard deviation that is 1. The histogram is not symmetric as the other one, but as you can see over here, that is not really good. Even the cumulative density function is not really good. And look at the probability density function, it's not good. We can see that even here we have a mean of 0 and a standard deviation of 1. The results of the transformation are not good. Then, for example, we can try a different values. Now we can put here, we know that we have, for example, 155 samples. And for each sample, the graph of the cumulative density function is going to change, right? Then we can think, okay, if we put here, for example, 120, we're going to have better results than if we put 42. But even we can put more, 140. But you can see that the results even are not good. Let's go to open, and let's go to make this one bigger. The results are not bad, are even better than with the other one. But this one is for 43 polynomials, and look at these results. The histogram is very symmetric. But with 140, it's not that symmetric. You know, the difference between the maximum and minimum are different. The mean and median, they are pretty similar. The standard deviation is also 1, but the histogram is not that symmetric, okay? But if we can make the things easier, why we want to use 140 polynomials when we can use 40 and the model is more simple? The simple that we can make the model better, because here the improvement of the results, it's not that good. You can see that the histogram is not that symmetric as this one, because here the difference is less. Then the thing I want to show you here, that even using less number of polynomials, the results are even better. And we can try a different number here. For example, let's go to put a small number. What happened, for example, with 30 polynomials? Because if we can reduce the number and we can get a good model, we can use 30 polynomials. We don't need to use more. As simple as the model, better it is. Then double click to open. But as you can see, with 30 polynomials, the results are not really good. Again, it's not pretty symmetric. And you can see the shape over here is not really good for the probability density function. If we compare with the 43 polynomials, you know, even the histogram is not really good. Then, you know, what you have to do is try different values for the polynomials to find the function that you want and the one that provides the better results, okay? In my case, it was 43 polynomials. I was playing with several numbers, and at the end I get that 43 was good, and that's the number I'm going to use for the transformation. But for each variable, the number of polynomials is going to be different. Remember that the number of polynomials that we are using is to fit this function over here. We want to adapt the shape of this graph. But what we don't want to do is overfit, because if we overfit, the results that we get are not good. Then we want something at the middle. We don't want underfit, but we don't want overfit. Then we have to try different number of polynomials to see what is the best result. Now, the last thing I want to do here is just put 43 polynomials again, because as I didn't take this one out, it modifies also the CSV file. And I want this CSV file to create the Kriging interpolation in the next exercise and also the simulations. Then I'm going to keep this one with 43 polynomials. Now with these values, over here we can do the simulations and the interpolations. In the next lesson we are going to see how we can use these values to predict the values in those locations where we don't have any sample with the simple Kriging, and then how we can reverse the transform values to the original scale. But that one is going to be part of the next lesson. Thank you very much for watching this video and see you on the next one.